So we are discussing synchronous generator, and last class we discussed we started synchronous generator, and we saw the equivalent circuit where we mentioned RA and XS. The XS is nothing but it is your XA plus XM we derived, right? So one component is because of the armature reaction we saw last time, right? And the phasor diagram we have drawn, right, considering the armature reaction as well. So please close the door. Okay, so today we'll talk more about the synchronous generator, where we'll see the power relationship, and then we'll talk about the characteristic of the generator, internal and external characteristic. Already you have done in your laboratory internal and external characteristic, that is OCC, ACC, right? And external characteristic, that is the load characteristics. Okay, so first we'll see the power relationships. So already we know that the input power we give to a generator is the mechanical input. So that we can write it as Ts omega S. Ts is the shaft power, that is a shaft torque from the motor or from the prime mover, you can say. So prime mover can be anything, like it can be a diesel engine, it can be a gas turbine, it can be a thermal turbine, a turbo or steam turbine or hydro turbine, right? Anything it may be. So the output of the prime mover, that is connected to the generator. That torque is Ts, shaft torque, and omega S is your speed of that is the synchronous speed of the generator, right? And then the net input power to the generator, we can say that the shaft input power from the prime mover, that is Ts omega S plus VFIF. VFIF is this is the input power to the field, right? Field winding. Though it is not very huge quantity, but it should be considered as an input power, right? VFIF. VF is the field, the voltage to the field, and IF is the current to the field winding. And then I can write the output power in terms of the terminal voltage and the current, load current or armature current, that is 3 VA IA cos theta. Why 3? Because VA IA, they are the phase voltage and phase currents. So VA IA cos theta is the phase real power into 3, that will give me the total output power of the generator, right? So theta is your load power factor, okay? Load power factor angle, and cos theta is the load power factor. And there are certain losses also. So copper loss we can write in the armature, that is 3 Ia square Ra, and therefore I can write the input power, total input power, right? P in is equal to output power. This is your output power plus losses. So this output power is thrice of VA IA cos theta plus copper loss in the armature. PR is your rotor loss, or we can say rotational loss, and PST is your stray load loss. We have never seen this term previously in case of DC generator, right? What is the stray load loss? It actually happens because of the load, electrical load connected to the synchronous generator. How it comes into picture? It is because of the harmonic content in the supply that causes extra burden on the generator, though it is very small, but it causes certain load. Okay, so it is because of the harmonic content in the generator supply to the load, because if we'll give a fundamental frequency supply to a load, it will have a different power as compared to a harmonic mixed supply to the load, right? So therefore this trail load loss is sometimes it is considered it is because of the harmonic content in the supply, and because of that the change in load is known as trail load loss, right? So although it is very minimal and it has very less impact, so this is trail load loss. Then VFIF, of course, it is the power we give input to the field, and that is the loss in the field, right? So then these are the constant terms. So we can say right now that PR, PST and your VFIF. This is a rotational loss. If your generator is rotating at constant speed, then I can say PR is constant. PST, trail load loss, also constant. I can assume if there is no fluctuation much, there is no transient much in the supply. Then VFIF is also constant, right? So then, considering these three terms, I can say that this is the constant loss in the system. So PC, that is represented by PC, and it is equal to PR plus PST plus VFIF, right? Okay. So now I can say that this is your power flow diagram in the synchronous generator. So we give input here Ts omega s plus VFIF, and of course VFIF is lost in the field winding as copper loss in the field winding, right? And then the remaining power, the shaft power only, that is transmitted to the generator, and then we have constant losses like PR and PST, okay, rotational and trail load loss. Then the remaining power we can say is the PD, that is the developed power, and it in fact it is from the developed power. If we'll subtract the copper loss in the armature, we'll get the actual output power of the generator, that is price of VIA cos theta, right? So this is your power flow in the synchronous generator, right? I hope till now there is no doubt. Why you all are coming late?
Sir, actually the cycle time got constant.
Oh. So then I can say the efficiency is power output by the power input, right? So power output already we know, that is 3 VIA cos theta, and power input we have derived in by substituting this. This is the expression for the efficiency in the generator, efficiency of the generator, right? Okay. Now from this equation we can obtain the condition for the maximum efficiency, that is criterion for maximum efficiency, as we have done earlier also. You have done for transformer as well as for the DC motor, DC generator, right? So can you find it? So this is just by taking the derivative d eta by dIA, I can get the expression and I equate to 0. I'll find the expression of this, okay? 3IA square RA equal to PC. So this will be your criterion for maximum efficiency. Okay? I hope everybody got this. Everybody got this? Now we'll see the approximate power relationship. Okay? What is this approximate power relationship? Here we are actually neglecting the resistance of the armature circuit. Okay, as you are seeing here the equivalent circuit of the generator here we are only considering the synchronous reactance, that is XS. We are neglecting RA, right? Okay. So now what benefit we'll get? We'll get an approximate power formula which will be very important in future study, right? So here you can say, we can see here that the phasor diagram, if we are drawing this phasor diagram for the lagging power factor, that is IA is lagging VA, we can see here by the angle theta, then we can see here that the EA can be drawn just by adding that EA equal to VA plus J of IA XS, right? So that is what it is drawn here, that your EA is shown, right? Now, if I will segregate EA into real and imaginary component, let us say delta is the angle between VA and EA. So this is the angle delta, right? Now considering this angle delta, if I will segregate EA into a real and imaginary part, then I can write EA cos delta plus J of EA sin delta, right? The first equation. Then if I will segregate current IA in real and reactive terms, then I can write IA cos theta minus J of IA sin theta because it is lagging. So this is your reference axis, right? If I will draw the imaginary plane here, this is your real axis, this is your imaginary axis, right? Okay. Now, so IA will be projected here in the imaginary part, in the negative part, so it will be minus J of IA sin theta, right? Okay. So now, if I will write the equation for terminal voltage VA, it is VA equal to EA minus J of IA XS, right? So then I'll substitute, if I'll just find IA from this equation, right? Then it will be EA minus VA by J of XS, right? Now I'll substitute the real and imaginary terms of EA, because VA is a real quantity, because VA we have taken as reference, so it is the real, it is in phase with the real, right? Real axis, so therefore VA is a real quantity here, right? So therefore EA minus VA by J of XS, and then just by manipulation we'll get EA sin delta by XS minus J of EA cos delta minus VA by XS, right? Now, if I'll write IA cos theta, because IA I have written IA cos theta minus J of IA sin theta, right? Now if I'll equate the real terms and reactive, or real terms and the imaginary terms, so then IA cos theta will become equal to EA sin delta XS, right? Okay. So now I can find the power relationship neglecting RA, so that will be PO will be equal to 3 VA IA cos theta. So instead of IA cos theta, I can write EA sin delta by XS. Just by substituting here, instead of IA cos theta, EA sin delta of an XS, I will get the expression 3 VA EA sin delta by XS. So what is delta? Delta is the angle between EA and VA, right? So that means sine of the angle between EA and VA, right? So this angle is known as power angle sometime, and sometime it is also known as torque angle, right? So this power angle is essentially very much important in our power system study also. 3 VA EA sin delta by XS, right? This is the expression for PA. Now if I will say, can you find the expression for QO? Because synchronous generator has the reactive power also, right? Reactive power component. So can you find this reactive power component, expression for reactive power component? So this will be 3 VA IA sin theta, right? So just substitute IA sin theta here. We have seen here IA sin theta will be here, this component, right? Just substitute here, you will find the reactive power component, okay? So what will be the expression? Can anybody tell? It will be 3 of VA. VA into EA cos delta minus VA. EA cos delta minus VA by XS. By XS, right? Okay. So this will be our expression for reactive power. Okay. Okay, now further if we'll draw the power versus this power angle, that is delta, so then it will look like this. You can see here. So if I'll plot this power output versus delta, it will be a sinusoidal, it will look like a sinusoidal signal, right? Because the sine delta term is involved, right? And we know VA, I, EA and XS, if we'll consider as constant, then I can write it as E max sine delta, right? So P max will happen at this point, that is pi by 2, when delta is equal to pi by 2. So this is your E max point, right? That is equal to thrice of VA, EA by XS. Okay, so this is this characteristic, or this curve is known as power angle curve, power angle characteristic. It is for the round rotor. If your rotor is salient in structure, salient full rotor, then your characteristic will little bit, it will tilt, okay? And we will not talk about much about the salient full machine here. Similarly, we can find the maximum power equation, that is PDM, or we can say POM, that is same 3VAEA by XS, and the TD maximum or TD equation will be just by dividing omega s. I will say this is your torque equation, 3VAEA sine delta by XS omega s, right? Because this delta term is coming in both expression, power and torque, so this angle is sometimes known as power angle and or sometimes known as torque angle. So power engineers generally they refer these terms frequently, power angle and torque angle. Okay. And then of course the maximum torque will be 3VA EA by XS omega s, right? Okay. So these are your equations of just for the approximation that we are neglecting the resistance in the synchronous machine, right? Okay. Now this is very practical synchronous generator tests. Already you have done this, few of you have done in your lab. Yes, OCC and ACC. So open circuit test and the short circuit test. So how you proceed in open circuit test, short circuit test? Before you proceed, what is the objective of open circuit test, short circuit test? What you do? You find the characteristic of open circuit test and short circuit test, both characteristic, SC characteristic and OC characteristic. With that, what you do? You find the ZS, right? Okay. So ZS you have to find in this. So ZS is consisting of two terms. One is your RA plus JXS, right? So XS we can find from this characteristic. Now RA how will find? How you obtain RA in your experiment? Multimeter. Okay, very good. Through multimeter we can find RA directly. So for that we need to, if your synchronous generator, so this is called resistance test, okay? And for that, in fact, we need to measure the resistance across the two terminals, any of the two terminals out of the three terminals of the generator. Suppose your generator is star connected, right? Star connected configuration, your armature winding is star connected, then how will determine it? you have to find the resistance across the two terminal. So in the sequence, how many measurements will be there? 3 measurements you can take, right? Okay. So, and that 3 measurement, you have to take the average of the 3 measurements. So whatever it will come, suppose let us say the average of the 3 measurement came RL, okay? Then the RA will be RL by 2, okay? Because if you will see the star connected circuit, your windings are like this, right? And these are the terminals, okay? And now you are measuring here through the multimeter. Then the measurement, whatever term will come, it will be twice of RA, right? Now RA will be RM by 2, right? So RM means measured value. Similarly, you can take 3 measurements because we have 3 alternative measurements you can take, and the average of 3 measurements you can first of all you can take. Let us say your RL is equal to RM1 plus RM2 plus RM3 by 3. RM1 is, let us say, the first measurement between A and B, okay, and RM2, let us say, between B and C, and RM3 is, let us say, it is between C and A, right? Then your average RL will give us the accurate result. Then you will take this RL, average of these 3 measurements, and find RA, which is equal to RL by 2.5 into RL, right? Now if it is delta connected, then what will do? Your generators in the lab is star connected or delta connected? Therefore you don't know, right? So if it is delta connected, what you will do? You have to also do the same measurements 3 times, right? And whatever RL you will get, RL is nothing but it is the measurement across a delta point, right? One side. Now, how will these are 2 parallel windings, two parallel in series, 1 in parallel, right? Then if you will resolve this, you will get RA equal to 3 by 2 RL, right? Just solve it, you will find it 3 by 2 RL. That means 1.5 RL, okay? So RA will be 1.5 RL, okay? So this is your resistance test through which we found the resistance of the armature of the synchronous generator, right? Okay. So now we'll talk about the open circuit test. Okay. So in open circuit test, what is the procedure? The procedure is to open the circuit and connect the voltmeter across the open terminal, right? And then you have to vary the field current from 0 and you will proceed gradually up to the rated voltage, or beyond the rated voltage you can go up to 50% more than the rated voltage, right? So how much you have gone beyond rated value? 50% beyond you go, 50% above rated value? No. How much? If you go to above rated value, 50% above rated value, then you will find actually a saturation, 25%. So this is your circuit for the open circuit test, right? So these are the 3 windings. This is star connected synchronous generator, and here we are putting the voltmeter across A and B phase, right? And here we have a variable voltage source to the field winding, okay? And now varying this voltage source, we can adjust the current here, field current, and that by that way we can induce the voltage. Generated EMF will be adjusted, right? It will gradually increase. So by that way we'll get this is your short circuit short circuit diagram, how we do the short circuit test. Here we short all the terminals of the armature circuit, right? And here we have a variable voltage connected to the field. Then what we do here, after running the generator in the rated speed, that means synchronous speed, what do? You have to vary the voltage here. We need not to see the rated voltage here, we need to see the rated current here, right? Short circuit current. So you cannot go beyond the rated current because it may burn the machine, right? So therefore we need to stick to the rated current. But beyond the voltage you can go a little bit, up to 50%. But current is very dangerous because it may burn the winding, right? So therefore the ISC should be sticked, this current should be stick to the I rated. Whatever the rated current, we must stick to that. Up to the rated current, this current is allowed, short circuit current, right? Okay, so by varying this voltage, we can get the short circuit. Then we'll plot the short circuit current versus the field current, then the open circuit voltage versus the field current. When you plot, we'll get this kind of curve. Have you plotted in your lab? Have you got this curve? Okay. So what here it is the actual OCC with saturation, right? And just if we'll plot a tangent to the OCC, you will get the air gap curve, or air gap line we call it, because it is an unsaturated curve, right? And so when there will be no saturation, we will get like this straight line, right? That is the voltage versus field current. And similarly, if we plot the short circuit current versus field current, you will get a straight line as well, right? But the scale will be different. Therefore, here the short circuit current is plotted right side. You can see the scale is different. Here the no load voltage, right? Now, under short circuit condition, how to find the ZS? Under short circuit condition, we know the terminal voltage is 0, right? Okay. Now your whatever EMF will be induced, that will be equal to ISZS, right? Or IAZS, you can say. IAZS, right? Okay. Now, so from the open circuit, suppose let us say under SC, this current, short circuit current, rated current of the generator, I got the field current, let us IFR. Now corresponding to this IFR, I can find the voltage, right? Okay. So whatever voltage I will get, okay, so that if I will divide with IA, then or ISC, I will get the impedance, right? So that means your EA by ISC under this condition particularly will give me ZS, right? Okay. Now after finding ZS, you can find XS as well, right? So I will find XS, ZS square minus RS square, right? So this will give me the parameters of the synchronous generator, RA, XS, right, ZS. Now the question is, this ZS, whatever we calculated, it will not remain constant throughout when we vary the field current. It will always vary, right? Have you done this test? Have you calculated this impedance and plotted it with respect to the field current? Huh? Have you done? So it will not remain constant, right? Why it will not remain constant? Because your EA is not constant, it is varying, right? So therefore your ZS also will not remain constant. Therefore it is very important that the parameter of synchronous generator doesn't remain constant throughout its operation. It depends upon the load. When the load current varies, then your ZS also varies. So this is a very important conclusion, where many times we take ZS as constant, but it has an impact on the ZS, which also impacts other operation in the power system, right? So you can see here the plot of ZS. versus IF, the field current. Okay, so when you plot it up to the unsaturated region, it may remain constant. Then after that, it will change, right? It will gradually decrease based on the saturation voltage, right? So it will gradually increase. So we are seeing this curve is not remaining constant. So you might have got in your laboratory experiment as well, right? Okay, this is all about your internal characteristic, or we can say this is OCC and SCC, right? And next is your external characteristics. So what is this external characteristic? External characteristic, already we have, this is the plot between the external parameters. Here the external quantities in the generator are VA and IA, right? So VA and, or you can say IL, or you can say IA. So they're same both. So if you plot VA, the terminal voltage versus the terminal current, then what kind of curve will, in case of DC generator, we have plotted for various generators, for shunt generator, for series, for compound, right? So we got different characteristics. Here also for synchronous generator, we'll draw it for different power factor angle for the load. Okay, so different power factor angle for the load, for unity, for lagging and leading power factor. Now you can see this characteristic. So you can see here, so this is your no load voltage, and this voltage gradually diminishes. For, let us say, consider first unity power factor equal to 1. This will gradually diminish. We'll see the phasor diagram as well. And similarly, for lagging power factor, it will drastically diminish the voltage, right? And for leading power factor, the terminal voltage will be greater than the voltage which is the supply voltage from the generator. Why for the leading factor we are getting this? Because of the capacitive effect, right? So this effect also we are feeling in our campus as well, right? Because all the supplies in our campus is through the cables, right? Underground cables. And we are not finding an overhead line here in our campus. So underground cables, in fact, they have more charging capacitance and as compared to the overhead lines. So when we have charging capacitance at the end or receiving end, that creates over voltage. Okay. So many times we have over voltage in our campus also, and that causes many equipment damaged condition. Okay. So this is because of the capacitive effect when the load becomes actually with a leading power factor, right? Okay. So we'll see here how it actually it happens. You can see this phasor diagram where we have assumed here the field current is constant. Okay, it is constant, and considering the field current constant, that means your generated EMF, that is EA, will remain constant throughout. So if we'll draw the locus for EA around it, it will give me a circle, right? Okay, it remains constant. Now your current, when your load current will increase or decrease. So this is for the unity power factor. Okay, so for unity power factor we are drawing this. Now the current will be in phase with the voltage, right? Terminal voltage. The load current will be in phase with the terminal voltage VA, right? Now we are neglecting here the resistance, impact of the resistance. So we know the equation VA is equal to EA minus J of IAXS, right? Okay. So in this case, when we draw it, so let us say the current will increase now. Your armature current increase. Then what will happen in this case? EA is constant, right? EA is remaining constant. If I'll increase IA, then what will happen? Your VA will decrease, right? Okay. Gradually it will decrease, and what will happen to this angle delta? Your delta will increase, right? So as you increase the load current, your delta will increase gradually. Therefore, this delta is sometimes known as power angle or torque angle, or it is sometimes known as the rotor angle also. Why it is known as rotor angle? Because as you increase the load on the generator, then what will happen? Your load, the speed of the speed of the rotor of the generator will gradually decrease, and this angle, in fact, it will increase more and more. So therefore, it is sometimes known as rotor angle and also power angle, right? So as this angle we can see in the next figure here. The next figure, the delta is increased with the increase in the current. We have increased the current, load current here up to this point. Now your VA is decreased and your delta is increased, right? Okay. But EA remains constant because it depends upon the field current, right? Similarly, if we'll take the lagging power factor load having lagging power factor, then we'll see the same impact almost, right? As your load current will increase, what will happen in this case? Your VA will decrease, of course, and what will happen to the delta? Your delta will increase or decrease? Can you do some analysis? What will happen to the delta? So first we are talking here magnitude. Let us first consider the magnitude increase. Keeping the load factor angle constant, let us say the current is increased. Here the current is increased, the delta is increasing, right? Here. Okay. But if your theta or power factor angle will increase, what will happen now we can see here. If your power factor angle will increase, your delta will decrease, right? Okay. But your voltage, of course, for both the cases, it will decrease. The magnitude of the voltage, terminal voltage, right? Similarly, if we'll take the leading power factor, for leading power factor, the terminal voltage will increase when the current magnitude is increased, right? You can see here, comparing both the figures, we can see the terminal voltage magnitude is increasing for constant power factor and increased magnitude of the load current, right? Whereas if your load power factor angle will increase, then your voltage is also increasing and your delta is decreasing, right? Your delta will decrease here. So in both the cases, for leading and lagging power factor, if your power factor angle is increasing, then your power angle, or you can say the delta, which is between EA and VA, is decreasing, but the voltage magnitude is increasing, right? So this is the conclusion we can say. And okay, we'll continue in the next class. We'll stop here. Okay.